want to talk about antenna design today because a lot of people think that, oh, you need to have a high power output transmitter to get far, which is not true. It also determines on your antenna and your coax type, and that's stuff that I want to cover today. Now, in the radio world, you have a radio wave, which is a sinusoidal wave, meaning it goes, from a positive to a negative point, okay, and that's measured by its frequency in hertz, which you might be familiar with if you're a computer person. Megahertz, gigahertz, kilohertz. A radio wave is measured in cycles per second, hertz. Hope I've got that clear to you by now. Now, you can't just take any piece of wire, just string it from point A to point B and say, oh, here's my antenna. Your antenna has to be specifically designed for your wavelength. Now, your wavelength is the distance between peak to peak on that sine wave itself, okay? Now, general rule of thumb is the higher your frequency, the smaller your wavelength is going to be, because if you have a certain amount of time and you add more frequency to that, your wavelength will shrink. So a higher frequency device like 2.4 gigahertz might only have an antenna, I think maybe 2.5 inches. I don't know all the calculations off the top of my head. But something like, say, 900 megahertz will maybe have like a 6 or an 8 inch antenna. Now you can actually design your antenna all the way down to like the kilohertz, or the just right down to like 4 decimal places, right down to the actual hertz. Now, there are different types of antennas. Okay, you have an omnidirectional and a unidirectional antenna, which are the two most common types of antenna. Now, an omnidirectional antenna is just like this light that's right above me. Okay, it is emanating an energy wave, in this case light, in 360 degrees all around me. Okay, a unidirectional antenna would be a lot like this flashlight. Now, this flashlight was designed to put a beam of light on a specific place. Now, let's say that this is a transmitter of energy, like a flashlight transmits light. Duh. Let's say my tablet PC back there is a receiver. Okay, now if this is a radio transmitter and that's a radio receiver, we're going to go and transmit to that receiver. Okay, and we have a relatively focused beam of light, or focused beam of energy. This is a unidirectional antenna. A unidirectional antenna focuses that radio energy in one specific spot. Now, everything behind us does not have light. It does not have radio energy, light energy, whatever analogy. Now, it is actually sacrificing direction for focus. But with focus, you get greater distance. Now, the further we pull back, the harder it is to focus because the target becomes smaller. So what you could do is you can widen your beam. But if you notice, the wider it gets, the more it dissipates over range. So we don't have as much range as if it was focused. So you have to understand that a unidirectional antenna will actually focus direction. It'll sacrifice direction for focus, but gain range. Okay? Now, a common type of regular omnidirectional antenna is a whip antenna, like on most radios or cars. It'll pick up a signal from every single direction. Some directional antennas that almost everyone is familiar with is satellite dishes. Now, this is called a parabolic dish. Basically, this dish right here has been designed where no matter where the radio signal hits will reflect to a common point, which is right here. Okay? Now, this antenna that I actually have on here, that's called a dipole antenna. A dipole is a very, very general purpose antenna. Basically, it is either, it's two wires either strung horizontally or vertically, depending on whether or not you have a horizontal or vertical polarization of your signal. Now, it seems complicated, but it's simply put. This is horizontally polarized. This is vertically polarized. That's it. It's either whether or not the elements themselves are going from left to right or up to down. Now, your signal has to be modulated within the frequency. Now, we're all familiar with AM, FM because of our radios, but there's also other things like constant wave, carrier wave, some people call it, and short sideband. We'll get into those another day. So now you understand that your frequency is directly proportional to your antenna. This thing has actually been designed to the wavelength of the FRS radios I used in the previous segment. Now, you're saying, okay, that's great, fine, and dandy, so what does it take to build an antenna? Metal. That's it. Metal is an absolute conductor and reflector of electrical radio waves. So like I said, this dish will actually focus all of the radio waves to this point. And this antenna, this dipole antenna, has been designed to receive the wavelength of my FRS radios. Okay. Now I've got something that any Wi-Fi enthusiast will understand is a Yagi antenna. Okay. Basically, each one of these elements will reflect the radio signal of that desired wavelength back further and further until it hits the dipole, which is then fed into your receiver, which is something else we have to get into. Coax. How do you get your radio wave from your transmitter to your antenna? Okay, that's where coax comes in. Now, if you have satellite or cable television, you'll understand what coax is, but not all coax is created equal. The stuff that you see on the side of your neighbor's house that hopefully right now you're not thinking about ripping off his home to go and use in your own antenna designs, that stuff's not going to work because it's 75 ohms. Now, if you remember basic Ohm's law, ohms is the amount of resistance that something can have. A 75 ohm cable is too great for a transmitter. However, for receivers, it's just fine. So if you have a scanner and your neighbor's got a bit of extra coax on the side of his house he's not using, I didn't tell you to take it. Now, you normally want to have 50 ohm coax cable feeding your antenna. Not all coax is created equal. Some coax is designed for lower frequencies, some coax is designed for higher frequencies. Example, RG58, which is the stuff that's found in the really old cable-based networks. That stuff really sucks at high frequency, absolutely miserable for Wi-Fi. You shouldn't even run it more than 3 inches. But for lower frequency stuff like 50 megahertz, 60 megahertz, that stuff is good. RG8, which is usually commercial grade amateur radio stuff, is pretty good. It can go up to about 500-600 megahertz, but the longer the run it, the higher the frequency, the crappier it's going to get. LMR 100 is great for high frequency stuff, but it's so thin it shouldn't be run in long lengths. LMR 400, which is like a really thick coax cable, can go up to I think 6 gigahertz or even higher. I'm not sure. I have to go and look at my notes. But either way, the thicker your coax, the more power you can output. So don't expect to get some spaghetti strong piece of coax and pump 50 watts through it without that wire actually melting in your hand. So there's actually a lot to radio waves when it comes to personal safety. Now, right now I'm only showing you antenna design, but later on we're going to get into transmitting. Definitely going to get into 2.4 gigahertz and Wi-Fi stuff, and you have to understand that the higher your frequency, the higher potential you have for doing bodily harm. The higher your power output, the higher you can do bodily harm, the greater the intent. I mean, the greater the possibility. Intent. But anyway. This is just some basic antenna design. I'll put in the show notes some links that'll go into greater detail. I don't want to overcomplicate this. Just want you to understand the different types of antennas. It does matter either focused beam of energy, which is a unidirectional, or an omnidirectional, and your coax type. It's the only thing I want, and frequency and all that crap. So anyway, I'm rambling on again. Either way, hit the show notes. I'll put some links that'll explain in more detail exactly how radio works and how to design a dipole antenna. Maybe, you know what? Just go on the forums and ask me what you need to know, and we'll put up whatever links you're interested. So, yeah. Don't kill yourself, and if you do, at least record it so we can laugh at you.